Hello and welcome to Diksha Karnataka YouTube channel. So now we are going to discuss about another important chapter, magnetism and matter. Now it is, if you see the weightage of this chapter, 2 to 3 questions from KCET and 5 to 6 marks in your PUC exam. You might think that, sir, this is a low weightage chapter. Why should I study it? But remember, this is a very easy chapter. If you just go through this chapter once, most of the concepts will be covered at one go. So that means if you just put a little bit of effort, say 2-3 hours, then this chapter is done and dusted. All the questions you can answer from this chapter. You just need to revise it once more before exam. Obviously we will do that. So if you are new to our channel and yet not subscribed to our channel, then don't forget to subscribe. What are you waiting for? Because all the chapters of your second PUC we are going to do in one shot in our channel. So don't wait, subscribe today so that we get the inspiration to make more videos apart from one shot and live sessions, etc. We will bring a lot more content to you. So that's why I request you subscribe to our channel, click on the bell icon, and also like this video if you feel that I am making some changes to your life, to your second PUC preparation. And remember, one very important part of your second PUC exam as well as KCET exam is that 50% weightage of your second PUC is directly related to KCET results, right? So that's why you have to, whenever you are preparing a chapter, you have to prepare for KCET and second PUC back to back so that you don't fall behind too much, right? Now let's see what are all the contents that we are going to discuss today. The bar magnet, the magnetic field lines, bar magnet as an equivalent solenoid, magnetization, magnetic intensity, as well as magnetic properties of material. So everything we will discuss in our session today. So let's start with a basic trivia about bar magnet. Okay, so we say that magnetism. So what is the meaning of this magnetism, from where this term came to existence? So it was a place called Magnesia in Greece. Okay, so the place called Magnesia in Greece, okay, that from that place actually first a natural magnet was discovered, and that's why it was came from magnesia, then it became magnet. Okay, so magnet refers to a something which was discovered from magnesia, right? So that's how the term came into existence. So the word magnet is derived from the name of an island in Greece called Magnesia, where magnetic ore deposits were found as early as 600 BC. Okay, 600 before Christ. So that was the time when it was first discovered, and since then it is with us, with our life altogether, right? So it is one of the most oldest thing that we still use in our life, right? Not the exact ore from magnesia, but the concept, right? So let's see what is a bar magnet. So bar magnet means we have a bar, chocolate bar, okay, then we have ice cream bar, right? So similarly bar magnet, okay. So bar magnet is basically shape of a bar, okay, and it has two poles. One is a north pole, another one is a south pole. Now what does it mean of north pole, south pole? Let us understand that the earth behave as a magnet with the magnetic field pointing approximately from the geographical south to geographical north. Okay, it is not exactly north to south, but for our approximation we don't go into the details about what is the angle, etc. So just think that, so this is the earth, this is our planet Earth. Assume for now that there is a magnetic field in the earth which points from south to north. Okay, this points from south to north like this. Okay, just rotate a little bit. So this is the earth magnetic field. So this refers to this is our south, this is our north. Okay, so when a bar magnet is freely suspended, bar magnet is the magnet which is shaped like a bar, bar ice cream, bar chocolate, okay, same thing. Obviously not as like us, you can assume this is like a small chocolate bar, okay. Say Now you are all familiar with the small chocolate bar that we used to eat, dairy milk. Okay, dairy milk is flat, so that kind of shape is also there, or say munch. Okay, more like munch, 5 rupee munch. So that is the shape of the bar magnet. Okay, when you suspend it, suspend means you tie up with a wire or some cotton thread, and then when you hang it up, it will rotate itself, okay, such that it points to the north south direction. So when you hang it, it will automatically point towards north south. When you keep it on a plane, it will not be able to rotate itself in the north south direction, but if you allow it to freely suspend it from the middle, then it will point in the north and south direction. The tip which points to the geographic north is called North Pole, and the tip which points to the geographic south is called the South Pole of the magnet. So when you suspend the magnet automatically point towards north and south approximately. It is the angle, you can find the angle. You can go on internet and find the angle between Earth's magnetic meridian and geographic magnetic meridian. You will find some angle is there, okay, some 10 degrees angle is there, but we ignore that angle. We say that it is almost on the same direction as north and south. And our sailors, ancient times, sailors, when they started sailing the seas, okay, they do not know that the magnet is not pointing towards exact north. So they believed that what is the magnet is pointing, that is exact north. So there was a northern star as well. So basically based on that, they decide the direction and their sail. Okay, so that's how they traveled across the globe, and that's how people discovered different countries, right? Columbus discovered America, okay, Vasco da Gama discovered India, right? So those are the things that how people connected in the sea routes. Land routes were there, but land routes are longer, right? Sea routes you can travel faster, much faster. So that's why sea routes was the route for traveling merchants. Okay, so merchants, most of the earliest ancient merchants used to travel on the road, Silk route. Okay, so this is one of the route from where the merchants used to travel. Now after that, here come the maritime route, which is the sea routes. Nowadays sea routes are still popular and it is being used by most of the shipping companies, right? We know that there was a conflict in the Middle East, and because of that oils are not being coming to India because it was coming via sea routes. So sea routes are still popular nowadays, and obviously the technology has changed. The most advanced technologies that they are being using in their ships. But yes, in the ancient time also, the most common use of a magnet was to find direction. So that means when you hang a magnet, okay, it will show you the actual direction, north and south, and based on that you say that this is the North Pole, this is the South Pole. Okay, so North Pole is generally denoted with a red color. So if you see a magnet, generally north and south is not written over it. The one half of the magnet is painted with red color, another half is painted with say black color. So the red color represents the North Pole, red color represents North Pole, the other half represents South Pole. Okay, now next, what? There is a repulsive force when north poles or south poles of two magnets are brought close to each other. So if you brought say a north pole of one magnet and north pole of another magnet, okay, forcefully together, you will see that they will repel each other. They will repel each other. Same as similar charges repel each other, okay, or like charges repel each other. Here we can say like poles repel each other. Okay, north pole repels. Okay, south pole, they will also repel. And if you bring opposite poles, same as charges, okay, north and south, they will attract each other. Okay, so same charges repel each other, opposite charges attract each other. Same here for magnetic poles as well. Similar poles repel each other, unlike poles attract each other. Okay, conversely, there is an attractive force between the north pole of one magnet and the south pole of the other, right? We cannot isolate north or south pole of a magnet. This is one of the most important point of this chapter. Just mark it down. In case of charges, we have single positive charge, we can have single negative charge, but in case of magnet, it is always attached to each other. They are made for each other, north and south, they are inseparable. Okay, you think, okay, I will cut it from here and I will get a separate north pole here, okay, and a separate south pole over here. You are wrong. Okay, if you cut it from here, you will see there is a south pole developed over here and a north pole is developed over here. So even if you cut a magnet, their property does not go away. You cannot even separate the north pole and south pole. Even if you cut it, okay, there will be a new south pole will develop, a new north pole will develop. So north and south are inseparable. So there is one important point. In case if you are able to create a single north pole, which is called magnetic monopole. Okay, magnetic monopole means it refers to the fact if you can create a single north pole or single south pole, that is called magnetic monopole. Okay, and in reality, magnetic monopoles do not exist. Okay, in case of charges, we have seen positive negative charges separately, also positive and negative charges together in case of a dipole. Okay, so positive and negative together in case of a dipole. So they basically can have everything, separate positive, separate negative, and combined together as dipole. Magnets are always dipole. Okay, magnets are always dipole, they do not exist separately. So magnetic monopole does not exist. Right? So this is very important point to remember. We will see that in future when we come across the magnetism, Gauss's law of magnetism. There is a very important point about it. We will see that. Okay, so if a bar magnet is broken into two halves, we get two similar bar magnets with somewhat weaker properties. Unlike electric charges, isolated magnetic north and south poles known as magnetic monopoles do not exist. So magnetic monopoles do not exist. Very important point to remember. It is possible to make magnets out of iron and its alloys. So there are few metals, namely nickel, chromium and iron. Okay, they can be converted into magnets. They are called magnetic materials. Okay, and some alloys of them are also can be used to create magnetic materials. Not all metals are magnet, by the way. Unlike in conductors, if you have seen, remember, all metals were conductors. Slightly good, slightly bad, but good. Overall, they are conducting electricity, right? But in case of magnetism, not all metals are magnetic materials. Okay, so here is a iron filing diagram of a magnet. So imagine you have a magnet behind this paper, okay, and you put a paper on top of the magnet and you sprinkle some iron filing. Iron filing means what? Dust of iron. You take a iron, you scrap it on top of it, and then you create some iron dust. It is obviously you are not supposed to do that in your home. Okay, it is done in the industry and it is sold as iron dust or iron filings. Okay, you take some iron filings, okay, you sprinkle it on top of this paper and then you tap it, then these iron filings will automatically align themselves like this, giving you this beautiful picture. You see that here some of them are concentrated over here, some of them are concentrated over here, and you can see this beautiful pattern. Okay, this is the same pattern as the electric dipole. If you remember, electric dipole almost had the same pattern, but there is a small difference in that. Okay, we will see that as well. The pattern of iron filings suggested that the magnet has two poles similar to the positive and negative charge of an electric dipole. So here, this is the one of them is positive, one of them is negative. Obviously, you cannot identify which one is positive, which one is negative from using the filing diagram. But you say this is one pole, this point is behaving as one pole, this point is behaving like another pole, and then you can say there are two poles present in a magnet. Okay, one pole is designated as north pole and the other as south pole. So which one? Now which one will be north pole, which one will be south pole? That depends on when you suspend it. Okay, suppose this one point towards north, so this will be north pole. This one point towards south, it is called south pole. Okay, actually in correct sentence it is called north seeking pole. Okay, it is seeking the north side, so that's why it is called north seeking pole. This one is called south seeking pole. Okay, so this is called north seeking pole, this is called south seeking pole. Okay, don't be confused, north pole, south pole, the concept remains same. The earth magnetism is not there, otherwise it still might have created a small confusion, but earth magnetism is deleted, so no need to worry about earth's magnetic field at all. Just remember, the one which point towards north is north, whichever is point towards the south is south. Very simple, easy, we all know that. Now one pole is designated as north, other as south. When suspended freely, these poles point approximately towards the geographic north and south poles respectively. A similar pattern of iron filings is observed around a current carrying solenoid as well. So if you have seen the solenoid, right, in the previous chapter, electromagnetic magnetic field due to current carrying wire chapter. This is called solenoid. It has a magnetic field B is equal to mu naught Ni, right? So if you have a current carrying solenoid, current carrying means you have to add a current to this. Okay, you will see the similar pattern. Okay, similar pattern, same as a north pole and south pole with a solenoid as well, right? Isn't it interesting? So you have this pattern, right? This is the pattern that we observe in case of this is the pattern that you observe in case of a magnet, and you have observed the same pattern for a solenoid as well. Not a super difficult pattern anyway. Okay, this is the pattern of magnetic field. This is the magnetic fields diagram. If they, in case they ask you draw a magnetic field diagram, this is the magnetic field diagram, same as dipole. Okay, this is north pole, this is south pole, and one important part which is not there in the dipole is this line. We will explain, give me a while. Okay, so magnetic field lines of a magnet or a solenoid form continuous closed loops. What is the meaning of continuous closed loops? So if you see that the loops are not broken, even if you are seeing that it is not there after this, basically it is there. If you continue with the loop, you will always see that the loops are continuous curves. Continuous curves means it exists inside and outside the magnet. Okay, so this is true for solenoid as well as a bar magnet. So there is a reason that is why called solenoid behaves as a bar magnet. In fact, if you put an iron core inside a solenoid, it behaves exactly like a magnet, and that gives rise to the electromagnet. So you have studied about it in the class 10th that iron core, there is a coil around it, it is called solenoid, and it is basically behaving like a magnet. Same here also, and it has a magnetic field as well. And if you observe the magnetic field lines that I have shown in the previous case, they are continuous closed line. Continuous closed line means if there is a one line here outside the magnet, the line will be closed inside the magnet as well. Okay, so inside the magnet there will be multiple lines. So if you see a line over here, it will be closed. Suppose it is going like this, it will be closed loop. Closed loop means each and every loop are closed. It is not like in case of electric field. If you remember, in case of electric field, if you draw the plot, it was like so this is my positive, this is my negative. Okay, electric field lines start at positive, end at negative. That's its end of the story, right? This is the single loop. Is it a closed loop? You start here, you end over here. Is it a closed loop? Obviously not. It is not a closed loop. It is not going back here. But when you take the same thing and if you replace it with the north pole and south pole, suppose this is north pole, this is south pole, it comes from north to south and then it goes back to south to north. Okay, so this is a closed loop. This is an example of closed loop. So in magnetic field, the loops or the field lines are closed, which is super important. The magnetic field lines of a magnet or a solenoid form a continuous closed loop. This is unlike the electric dipole, where these field lines begin from positive charge and end on the negative charge or escape to infinity. Okay, so in magnetic field lines, no field line escape to infinity. Each and every line escaping the north has to come back to south, and from the south it has to go back to the north inside the magnet. Okay, so if 100 lines are exiting the magnet from the north side, 100 line has to come back to the south. Okay, and inside the magnet it has to go from south to north as well. Okay, so this is a complete cycle. Okay, so loops are closed in case of magnetic field. Okay, the tangent to the field line at a given point represents the direction of a net magnetic field B at that point. So if you have a magnetic field line, if you draw a tangent, this gives rise to the direction of magnetic field at that point. Obviously magnet gives rise to magnetic field, right? Current carrying wire gives rise to magnetic field. So magnet is naturally supposed to give you a magnetic field, right? So when you are considering a magnet, the magnet produces magnetic field. Okay, and that magnetic field is represented by magnetic field lines. So these are all already we learned about this in our first chapter, right? So a magnet naturally have magnetic field lines. So when you consider a field line which is covering a magnetic field, okay, it is a curved line. How to find the direction of magnetic field at a particular point? You need to draw a tangent. Okay, curved line, you need to draw a tangent. What is a tangent? Tangent touches the line at only one point and it is perpendicular. If you can find the center, if you draw the center, it will be perpendicular to the center. That is the definition of the tangent, right? So when you draw a tangent, that tangent actually gives you the direction of magnetic field. Obviously if the magnetic field is in this direction, okay, the tangent drawn in the same direction, similar sense, okay, will give you the magnetic field's direction. Larger the field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. So these points are also valid for electric field lines, if you remember. Okay, so if the field lines are closer to each other, okay, then that represents a stronger magnetic field. If field lines are further apart, that gives rise to a weaker magnetic field. So if here we define it that the field lines crossing a unit cross section, if the more number of lines crossing the unit cross section, okay, that gives you a stronger electric field. If the same unit cross section, if less number of field lines are crossing, okay, then we say this is a weaker magnetic field. This is a strong magnetic field. This will be a weak magnetic field. Okay, so stronger means 5-6 people are coming together and saying that I demand this. Okay, that is stronger. And one people saying we demand this, one person is saying I want this, I want chocolate. That is weak, right? Strong means we want chocolate, we want this, right? We want a holiday tomorrow in your college. Don't do that. Just giving you an example. So if more people are together, okay, that gives rise to a stronger magnetic field. And if only one of them is there, then it gives rise to weaker magnetic field. Okay, the magnetic field lines do not intersect, same as electric field, same as properties of equipotential surface. Magnetic field lines do not intersect each other no matter what, same as electric field as well as equipotential surfaces. Okay, for if they did, the direction of magnetic field would not be unique at the point of intersection. So let me give you the idea once more. I discussed in electric field chapter, but let me tell you once more. Suppose this is the one magnetic field coming from this side due to one magnet. Here is another magnetic field coming from this side due to another magnetic field. Now at this point of intersection, what will be the direction of magnetic field? This one will say, no, I am the boss, I will have the magnetic field here. The other one will say, what I have done, I am also here, I will also carry the magnetic field in my direction. So magnetic field, there will be two magnetic fields direction at this same point, which is not possible because magnetic field is a vector. A vector has only one direction. Magnetic field is a vector quantity. The vector has only one direction, not multiple direction, right? So but here at this point of intersection the direction is not unique. So what will happen in practical, is this not possible that we can bring two magnets together nearby each other? Yes, it's possible. So what happens to the original magnetic field? That is one question that I like to answer here. So basically what happens, they gets added vectorially. They get added vectorially and you get a resultant magnetic field. Okay, you get a resultant magnetic field line as well. You get a resultant magnetic field line as well. So you will not see these individual lines, you will only see this line. Okay, so that means when two field lines are supposed to cross each other, you will not see their crossing, you will see the resultant magnetic field line. So this one no one tells you. Okay, this one everyone says the two lines cannot intersect. But what happens if they are trying to intersect each other? They reorganize such a way you see the resultant magnetic field line, you do not see the individual field line. So that's why two magnetic field lines can never cross each other, because even if they did, actually you will not see that, you will see a resultant magnetic field, because like two vector quantities can be added, you can also add two magnetic fields, and magnetic field lines represents only the resultant field, not the individual fields. So resultant fields only you will see, so they will not intersect each other. Very important and easy point to remember. Now bar magnet as equivalent solenoid. Okay, so equivalent bar magnet solenoid behaves like a bar magnet, right? We have seen that if you if you use bar magnet and if you put a solenoid, they both have the same magnetic field pattern, right? The same pattern we have seen few slides back, right? So this is the pattern, right? This is the bar magnet, this one is for solenoid. You see the almost same pattern for bar magnet as well as for a solenoid. So they behave, they are actually cousin brothers, you might say. Now if you put a core inside a solenoid, they also becomes it also becomes a magnet, and the magnetic field due to a solenoid is given by B equals to mu naught by 4 pi 2m by r cube. You remember where it came from? It came from the magnetic field of a coil. Okay, magnetic field of a coil, and that is a single coil. Okay, if you have a coil over here, you are trying to find magnetic field due to this coil at some distance, say x, and one condition was definitely there, x is super huge than the distance, right? In this case, this equation turns out like this, and if you compare it with the electric field equation, it was 1 by 4 pi epsilon naught 2p by r cube. Right, the equations are same, only instead of P we are using M, and obviously it was magnetic field constant, it was electric field constant, right? So that means this behaves like a magnet. Magnetic dipole is a magnet. Magnetic dipole, what is the magnetic dipole means? Magnetic dipole means a small magnet. Magnet is slightly bigger than a dipole. Magnet is also a dipole. Obviously di means two, pole means two edges. Okay, so if you have positive and negative together, it's called a dipole. North and south together, it is also called a dipole. But normally dipole refers to a small size. Okay, so a coil also behaves like a dipole, and if you can extend it to a longer period, that is a solenoid, you can create a magnetic field, and that magnetic field turns out to be constant inside this solenoid. Okay, so now and that magnetic field inside a solenoid is given by B equals to mu naught Ni. Okay, that is the magnetic field inside the solenoid, and this can be proved using Ampere's law, which is not there in the syllabus, this derivation anyway. So this can be done using this. B is equal to mu naught Ni. Okay, N is number of turns per unit length. Number of turns per unit length. These things we have done in our previous chapter. So if you want a detailed explanation of everything, you can go and check that out. Just we are revising the same concept once more. Next, similar to a electric dipole kept in an external field, if we keep a magnetic dipole in an external field, magnetic dipole is represented like this. This is basically a small needle, magnetic needle, okay, which looks like this, okay, like a Kaju Katli. Okay, slightly longer version of the Kaju Katli. This painted side is north the unpainted white side is south. Okay, so this is the north side, this is the south side. Okay, it makes some angle. There is an external magnetic field B. Now this will experience a torque when you keep it in the magnetic field, same as electric dipole experiencing a torque in an external electric field. Now what is the expression for torque? Torque is given by, if you remember, same. You don't need to memorize these things separately with the electric field. If you remember one of them, you can recall both formulas. Okay, in case of electric field, the torque was given by P cross E, right? P was electric dipole moment, E was electric field. In case of magnetic field, okay, in case of magnetic field, the torque is given by M cross B. M is magnetic dipole moment and B is magnetic field. Here M is total magnetic dipole moment. Generally small m, if there is only one loop, we use small m. If there are more number of loops, we use capital M. That is the difference. Okay, small m, generally if n number of loops are there, M is n number of loops into small m. Okay, or say n number of loops into small m. That is the basic difference. Otherwise nothing, no difference between small m and capital M. The potential energy stored in the needle. What is the formula for potential energy in case of electric field? Potential energy in electric field was given by minus P dot E or P cos theta. Same here. Magnetic field, it is minus M dot B. Okay, negative sign signifies work is done work is done by the field and not by the external force. So that is the same as electric field as well. Okay, P dot E, it is M dot E. Okay, or MB cos theta. So remember, this is minus MB cos theta. Now, where most of you are expecting question based on this formula, once there was question based on this formula. Same thing. Okay, angle 180 degree, the potential energy is maximum. Angle 90 degree, potential energy is 0. Angle 0 degree, potential energy is minimum. So everything is same. So you have remembered everything for electric field. You ignored it, and in the exam the question came in based on magnetic field. Now you are scratching your head, sir, I did not study magnetic field. What to do? Same thing. Same thing. Don't need to worry about it. If you have studied electric field, you will be able to study magnetic field as well, right? No need to worry that, sir, only electric field I know, magnetic field I do not know, then what to do about it. Now let's move on. If a bar magnet of magnetic moment M is cut along its length in two equal parts, then what will be the change in magnetic moment of the bar magnet? Remember, whenever you cut a bar magnet, you can cut a bar magnet in two ways. Okay, along the width or along the length. Okay, no matter how you cut a magnetic moment, if you cut it in two halves, both halves will have the half of the magnetic moment. If you cut it now individually, magnetic monopole strength etc. can change, but remember, if you cut it like this, also this one will have M by 2, this one will have M by 2, and if you cut it along the length like this one will have M by 2, this one will have M by 2. Okay, these are separate magnets, this is also separate magnet, this is one magnet, magnet 2. So in each cases, whenever you cut a magnet, okay, if you are cutting in two halves, each half will have M by 2. Okay, now if you take one of the halves, nowadays the questions are getting slightly trickier. You take one of the halves and if you cut it in another two halves, then what will happen to each of the halves? It will be M by 4, this will be M by 4, but this half will still be M by 2. Okay, remember, so it will be based on how many pieces you are doing. Okay, it will be based on that. Okay, it will not be M by 3. If you cut a single magnet into 3 equal parts, each of the parts will have M by 3. If you cut a single piece into 4 equal parts, it will be M by 4. But if you cut it half, then cut the other half into two halves, it will be M by 4 for those two halves. So just be careful, read the question based on the language of the question. You should be able to answer these questions very easily without any difficulty. Now, so far, if you have understood, please mention in the comment below, sir, I have understood everything. And I want to show you something which is very important for you, your preparation for your board exam, which is our free YouTube batch. If you want to join along with notes, then you will get the notes, you will get the all the lecture PDFs, then assessment, assignments, etc. You just need to visit any of our video. For example, this video, okay, you go into the description section of this video, click on here, join free ACE KCET course now. Okay, once you click over here, you will see that the price of this course is only 0 rupees. Click on here, buy now, and you will be landed to our free course. Okay, you can see some live and upcoming things are there. There is a question also. This is a you can see this is a test added in this series recently, so you can attempt the test. 14 questions are there. Okay, soon there will be many more questions will be added. Okay, and class notes, okay, quizzes are also being added here, so everything will be provided here to you. Okay, and it is absolutely free of cost. You don't need to pay a single rupee for this, which is the most important point, right? So who don't enjoy something free? So just join, click on the link given in the description section of this video. Okay, join free ACE KCET batch. There all the lectures that you are doing, including this lecture, its PDF, etc., will be provided in that session only. So do join it today if you have not yet joined. Right now, let's continue with our session. Next, so just comparison between electric field and magnetic field, which is a very quick analogy. So dipole moment in case of electrostatics, okay, the constant is given by 1 by epsilon naught. Okay, 1 by 4 pi epsilon naught. So the constant is 1 by epsilon naught. For magnetism, the constant is mu naught. It is mu naught by 4 pi. So 1 by 4 pi epsilon naught. Here it is mu naught by 4 pi. So 4 pi in the division is common, right? Only here it is 1 by epsilon naught, here it is mu naught. So 1 by epsilon naught and mu naught are respective constants. Dipole moment in electric field is denoted by P, right, which is basically the charge into the distance between them. In magnetism, it is denoted by small m. Okay, for a single dipole, it is small m, which is actually magnetic monopole strength into distance between them. The magnetic monopole strength is immaterial. That's why we generally, in case of, even though in case of electric field, we can say charge into 12. For magnet, we generally do not use magnetic monopole strength. Okay, equatorial field for short dipole. So minus P by 4 pi epsilon naught r square. Obviously r cube. Obviously there is a negative sign. Here also the same thing. Mu naught m divided by 4 pi r cube. So 4 pi r cube is same. 1 by epsilon naught, you replace it by mu naught, and P you replace by m. Formula remains same. You do not need to remember a separate set of formula. Only one correction you need to remember is that in electric field 1 by epsilon naught is there, in magnetic field mu naught is there. That is the only change, otherwise everything is same. Axial field for a short dipole, 2p into 4 pi epsilon naught r cube. Here it will be mu naught 2m by 4 pi r cube. Okay, external field, torque acting on a dipole in an external field, P cross E. Torque acting on an external field, magnetic dipole, M cross B. Okay, external potential energy, minus P dot E, it is minus M dot B. Now there was one question which came in your electricity chapter, electric charges chapter, that if the field is uniform, the external field is uniform, okay, then if you keep an electric dipole, what will be the force, what will be the torque? There will be a torque but no force. If the field is not uniform, there will be a force as well as a torque. Same question was there in magnetism as well. Non-uniform magnetic field, you keep a dipole, okay, what will happen to the dipole? It will experience a force as well as a torque. So everything related to electric field can be applied in case of magnetic dipole as well. That's why this chapter is easy. Basically, it's you feel like it's a duplicate, copy-pasted chapter from electric charges, only the dipole portion. From dipole portion onwards, it's like a copy-pasted part, right? Formulas are same, only the constants are different. Obviously, something has to be different, right? Otherwise, What do you think? Why there is a separate chapter for it? Electricity is slightly different, magnetism is slightly different. But in future, if you study physics in future, you will study electromagnetism, where electric field and magnetic field are not treated separately. They are combined together in a single branch of physics, electromagnetism. Okay, we have one chapter related to that, very small chapter, but we will see that there. Now here is one question. Figure 5.4 shows a small magnetized needle P placed at point O. The arrow shows the direction of its magnetic moment. The other arrows show the different positions. Okay, so here point P is the original magnetic dipole. Okay, original magnetic dipole. Okay, so a magnetized needle P placed at the point. So this is the direction of the magnetic dipole moment. Okay, the other arrow shows the direction of its magnetic moment. Okay, so magnetic moment at different points, it is shown by this arrows. Okay, different positions and orientations of the magnetic moment of another identical magnetized needle Q, in which configuration the system is not in equilibrium. The system is not in equilibrium. So what is the condition for equilibrium? Okay, so here is a circle. That means the distances are same. Okay, distances are same. Okay, Q1, Q2 are actually placed on this distance only. Now they are saying which case the system is not in equilibrium. System will be in equilibrium. First of all, what are the conditions for equilibrium? Conditions for equilibrium. First of all, the torque must be 0. If torque acting on it is 0, then it is equilibrium position. Now there are two types of equilibrium. One is stable equilibrium, one is unstable equilibrium. Stable, but here they are not talking about stable or unstable. So that is one thing very clear. So only thing they need to find in which of the positions the torque is 0. Okay, so we have to find the angles. So what is torque? If you remember, torque was M cross B. For a single dipole, it is M cross B. So torque scalar wise MB sin theta. So you need to find the angles and see and which of the cases sin theta values are 0. So if the sin theta values are 0, then we will say that system is in equilibrium. Now just for your slight convenience, maybe this circle is not super clear, so let me draw the circle once more. Okay, so this is the circle, and as you can see there are so these are the magnetic dipoles. Okay, this is the second dipole. Q is a second dipole. Okay, P is a primary dipole which is fixed. Q you are placing and you are saying that okay, the system will be in equilibrium or not. So first you need to find the magnetic field due to this dipole. Magnetic field due to this dipole at individual points. So you are given the second dipole is clear. Second dipole is clear, but you need to find the direction of the magnetic field. So P is the cause. This is the cause. Okay, this is creating the external magnetic field. So if P is given like this, P is not always in this direction like that. Okay, especially for these two positions. These positions, P is here. Okay, this is say P4, this is say P6. So along the axis, the direction of magnetic field is very straightforward. It is in the same direction. Along the perpendicular direction, if you remember, for an electric dipole, if you remember electric dipole, so this is a positive, this is a negative. Electric field was from negative to the dipole moment was from negative to positive, and electric field on the axis was in this direction. So even though P is in this direction, okay, along the axis dipole moment is in the same direction as the dipole moment. Okay, electric field was in the same direction as the dipole moment. Same logic we can apply for magnets as well. If this is a magnetic dipole, if this is a magnetic dipole and this is the magnetic dipole moment, magnetic dipole moment is in which direction? It is from south to north. It is from south to north. Okay, The magnetic dipole moment is pointed from south to north. So if you try to find the magnetic field along the axis, the magnetic field will be in the same direction of the dipole moment, and in the perpendicular bisector, the magnetic field will be in the perpendicular opposite direction. So here if you see, so this direction and this direction, they are in the same direction as this, and here what will be the magnetic fields? The magnetic fields will be, so here it will be opposite, here also it will be opposite. Okay, so along the perpendicular bisector, along this axis, it will be different. Otherwise the magnetic field will be in the same direction as that arrow. So this is the original arrow, OG arrow. So because of this OG arrow, whatever is the magnetic field that is shown, the direction is important. This is creating the external magnetic field. Okay, once these directions are done, this arrow is no longer required. Now we will individually inspect these positions. First point, you have to identify what is the magnetic field due to this. So magnetic field due to this is now done. Now let us look. What is the angle over here? Angle over here, so this is one arrow is in this direction, another arrow here. So theta is 180 degrees. Theta 180 degrees means sin theta 0. Here same direction, so theta is 0. Theta 0 means sin 0 0. For Q5 again theta is 180. This is equilibrium. Here Q3 theta is equals to 0. So this is also 0. But what about Q1 and Q2? For Q1, okay, this is 90 degrees, sin theta 1. For Q2, theta is again 90 degrees. This is also 1. So Q1 and Q2, the magnet is, the dipole is not in equilibrium. So PQ1 and PQ2, it is not in equilibrium. PQ1 and PQ2, it is not in equilibrium. In each and every other places, torque is 0. So that means those positions are actually equilibrium position. Easy question. We will repeat these questions once more in our journey. We have this question once more, so we have a chance to revisit this question once more. Don't worry, we will be solving a lot of MCQs from this chapter, because this chapter has 2 questions as one marker for your PUC, right? So we will be doing a lot of MCQs from this chapter, so don't worry, don't go anywhere. Let's continue with our discussion with magnetism and Gauss's law. Again, same Gauss's law, that is electricity, that's similar to that of electricity, with a twist. What is the twist? The net magnetic flux through any closed surface is 0. In case of electric field, if you remember, it was net magnetic field to a closed surface was given by Q upon epsilon naught, right? So right hand side was not 0, because charges can be, we can have single positive charge, we can have single negative charge, right? But in case of magnets, it is not there. Magnetic field is always exist in pairs. So this is consequence of the fact that magnetic field lines are closed and no magnetic monopole can exist. Okay, no magnetic monopole can exist. That's why B dot ds through a closed loop is always 0. B dot ds in a closed loop is always 0. That is a super duper important point. Remember what? Now there is a question. Which is one of my favorite questions. Suppose we have a Gaussian surface. Okay, we have a charge plus Q. We have a charge minus Q. Okay, what is B dot ds here? Okay, and we have another surface. We have a north pole, we have a south pole. What is B dot ds here? So this question did came in your KCET exam once. Okay, the question was like that, and they asking what is B dot ds. Remember, in case of Gauss's law, only the charge which is enclosed, that is conserved. So that means it will be Q upon epsilon naught. No matter what, it's a part of a dipole or not, does not matter. In case of magnet, you will not be doing that like that. It will always be 0. So this is a huge difference in case of magnetism and electricity. Now why it is so, I will explain it. So in case of, suppose you are considering electric field lines, the field lines are going out, okay, from positive to negative. No one will teach you this, no one, I guarantee that, okay. So magnetic field lines are going out, so electric flux, some electric field lines are going out in this direction, some is there, some is going here, so some electric flux is passing through this surface. So B dot ds equals to q upon epsilon naught, right. Net flux is not zero through this surface, so it is not zero. But if you consider a surface which is completely enclosing the dipoles, for example, there was one more question where this type of question was asked, plus minus, okay, plus q minus q. This case B dot ds equals to 0. B dot ds equals to 0 because total charge enclosed was 0. Now what about magnets? Why we are not using magnetic monopole even in this case? That is one super important point, that north pole is magnetic field lines are going out, but they are also coming inside the magnet. This is not there in case of a dipole or a charge, specifically for charges. So the reverse motion of electric field lines are not there in case of charges. That's why even if you enclosed only one charge, it will still be B dot ds equals to q by epsilon naught, and when you enclosed only one pole of the magnet, it will still be 0 because net flux is 0. So suppose one line is going in, one line is coming out. So basically flux measures how many field lines are going across the surface, and then they divide it by the surface and they call it the flux, right. So in case of magnetism, the net field lines, number of field lines crossing the boundary and coming back in is exactly same. So if 10 lines are going out, 10 lines has to come in, so net magnetic field through a surface is 0. So that's why the magnetic Gauss's law of magnetism says that B dot ds equals to 0. I just made a mistake over here, it will be E dot ds. Okay, it will be E dot ds. Okay, so here if both the dipoles are present inside, charge enclosed is 0, so E dot ds is 0. But if only one pole is enclosed by the surface, still the magnetic field will be 0 because it is a closed loop. Magnetic field lines are closed loop. Magnetic monopoles do not exist and magnetic field lines are closed. That's why in Gauss's law, B dot ds is always equals to 0 no matter what. So this is a trap that might be coming on your way very soon. Be prepared, it will be 0 no matter what, right? Now let's continue with our discussion. So now let us continue with another concept, magnetization. So a circulating electron in an atom has a magnetic moment. So if you have, say, an atom, okay, which is orbiting in a atom. So atom means there is a positive nucleus, electron is negative, so it is orbiting like this. So that electron orbiting around this have a magnetic moment. Each atom, okay, each electron have a magnetic moment. Let us understand this. If you understand this once, your entire life it will be cleared. Okay, in a bulk material, these moments add up vectorially. Suppose if I consider this is the motion, so this is the, suppose for example, magnetic moment is in this direction. This is a molecular or electron wise dipole moment. Okay, sorry, not dipole moment, electric dipole moment, magnetic dipole moment. Okay, these moments add up vectorially. Vectorially means suppose one electron is orbiting in this direction, you are having a magnetic moment like this. In the another atom, okay, the same material, okay, in a bulk material obviously there is not a single atom present. There are in 1 mole of material there are n into 6 into 0 to 3 into 10 to the power of 23 number of atoms present, right? So each of them have multiple electrons. So one electron orbiting in this direction will have a magnetic moment in this direction. So they are adding up vectorially based on the direction of different magnetic moments. You have to add them vectorially, vector addition, that's it, plus minus, or you take the what should I say, you take the components of the individual vectors, add them, but yes, obviously you don't need to do that, but understand the concept. Magnetic moments always adds up vectorially because it's a vector quantity. Clear? Now these moments add up vectorially and they can give a net magnetic moment which is non-zero. So far we are discussing about magnets, magnetic moment, etc. Now we are discussing about materials. Slowly we are transiting from normal magnets, we are now transiting into materials, right? Gauss's law also talks about magnets or magnetic dipoles, etc. But now we are basically switching. So that switching you have to understand. So far we are discussing about magnets, magnetic moment, magnets, magnetic moment. Now we are talking about atom. Okay, we are talking about materials, bulk material, right? So the context has changed a little bit. Magnetization capital M of a sample. Sample means obviously you have an iron or copper or any other material. So magnetization M of a sample is defined as the net magnetic moment per unit volume. This is net magnetic moment per unit volume. M is a vector quantity with a dimension L to the power -1 into A and is measured in units of ampere per meter. So the favorite question of the examiners, what is the unit of magnetic moment? What is the dimension of magnetic moment? Right? If you remember, magnetization or simple magnetic moment for a single magnet, single dipole, magnetic moment of a single dipole was given by NIA, right? National Investigative Agency. We did that. Let's do that once more. Current is given by A. N is the dimensionless quantity, is only a number. A current is denoted by A. A is denoted by L square. So dimension of M is AL square. Now magnetization on the other hand is given by M by V. So this is the total magnetization. You have to do the, this is for a single dipole. Okay, single dipole, suppose this is a single dipole, but in a bulk material there are multiple such dipoles. You need to add all of them vectorially and that is denoted by, say, M net. Okay, so the dimension wise it is same because all of them have same dimensions, right? So dimension wise they are same. Now you are trying to find the magnetization, okay, and magnetization is given by this. So what is the dimension of magnetization? Dimension of magnetization is basically AL square divided by, what is V? V is volume. Volume means L cube. Volume means L cube. So that is AL square by L cube, that is AL to the power -1, and its unit is A for ampere and L for meter, so ampere per meter, okay, or AM to the power -1. Okay, so this is called magnetization of a material. Okay, if this is a non-magnetic material, magnetization most likely to be 0, right? If it's a magnetic material, magnetization is not 0, right? The ratio of magnetic field at the center of a current carrying circular coil to its magnetic moment is X. If the current and the radius both are doubled, the new ratio will be, let's figure it out. So a ratio of magnetic field at the center of a current carrying coil. So this is just a, I think this question should have been a little bit earlier. Anyway, ratio of magnetic field at the center of a current carrying circular coil to its magnetic moment. So what is the magnetic field at the center of a current carrying coil? It is given by mu naught by 2 I by R. So this is the formula for magnetic field at the center of a magnetic current carrying wire. What is the magnetic moment? Okay, circular, one single coil, so magnetic moment is given by IA. N is 1. Okay, National Investigative Agency, but national is 1, so only IA is there, Investigative Agency. So now they are saying that this ratio is X. If the current and current and the radius both are double, then what will happen? Let's see. So B by M is what? B by M is equals to, I don't know what is happening. So B by M equals to mu naught by 2 I by R divided by IA. So I cancels and you get mu naught by 2 1 by AR. Now AR, what is A? A is area. A is area, that is pi R square, right? If you put that over here, you will get mu naught by 2 1 by pi R square into R, that is mu naught by 2 pi 1 by R cube, 1 by R cube, right? So if you see that in this expression, current is not at all there, only it is dependent on the ratio 1 by R cube. So this is the value X. Okay, now question is, if the current and radius both are doubled, the new ratio will be, so if you double the current, no change happened, but if you double the radius, then it will become X by 8, because if you double the radius, new X will be the some constant mu naught by 2 pi, okay, 1 by 2R whole cube, that is 1 by 8 mu naught by 2 pi 1 by R cube, right? 2R R whole cube is 1 by 8 R cube. So this is the X value, so it will be X by 8. Another interesting question, super duper funny question, right? If you really want to answer those questions, you have to be a little bit inquisitive, you have to be a little imaginative, and try to figure things out on your own, then only you will be able to answer. As you can see, mathematics wise nothing there, you just need to remember two easy formulas and just simplify as quickly as possible. Now let's move on. Now magnetic intensity, magnetization, etc., they all come for a material. Okay, magnetic field itself does not require any material. Okay, magnetic field can exist in space, but magnetic intensity, magnetization, they are all happening inside a material itself. Okay, so if you have, say, a magnetic field outside is B, okay, and you are trying to there is a material, okay, say A, whatever the magnetic field inside, okay, that how to measure that? That is measured using this quantity, magnetic intensity. Okay, how much of the external magnetic field is affecting this material. Okay, that's why it is generally for free space, it is given by B by mu naught minus M. Okay, B by mu naught minus M. Okay, so dimension of H is same as M. So dimension of H is same as M, that is AL to the power minus 1, and unit is same, ampere per meter. Now if you take this M on this side, add mu naught, you get B equals to mu naught H plus M. Okay, so when you apply a magnetic field to a material, what happens is that that material partially magnetized and remaining basically is given by this H vector. Okay, so when you apply some magnetic field, some north pole, similar to that of a dipole, right? When you apply electric field to a polar material or non-polar material, partly it is polarized and partly it remains unpolarized, and it reduces the external effect of the magnetic field. Same thing over here as well. Okay, we can measure that. So B is the external magnetic field that you have applied, H is the magnetic field developed within the material, and M is basically the magnetization of the material. So the material try to orient themselves in the direction of the magnetic field. Now based on materials to material, it can be positive, negative, 0, etc. Let's see. Now another quantity is magnetic susceptibility. Magnetic susceptibility means if you apply external magnetic field, how much you can influence the matter with it. Okay, how much influence you can make inside the matter so that it will magnetize on its own. That is called susceptible. Okay, susceptible means it is vulnerable. Okay, it is quite susceptible. So if you apply magnetic field, immediately you get aligned. Okay, so some friends comes and tells you, bro, today we have to play Free Fire against these groups. Arey, I will go, I will play. So you are susceptible to that. You are not thinking that, okay, 1 year, in another 7-8 months, I have a KCET exam, I have a PU board exam. You are super susceptible. You are saying, okay, I have to go, I will play, without thinking anything. That is susceptibility. Okay, don't be a susceptible material. You have to have some low susceptibility. Susceptibility low is better. So susceptibility is a dimensionless quantity. Okay, it's a dimensionless quantity. It's appropriately called magnetic susceptibility. It is a measure of how a magnetic material responds to an external field. If it is responding strongly, high susceptibility. If it is responding weakly, it is a low susceptibility. So magnetization depends on susceptibility. It is related by chi into H. The symbol is called chi. Okay, not chi, chi. Okay, chi. Now magnetic intensity is given by B is equal to mu naught H plus M, and M is given by H into chi. So now if you take that, you will get mu naught 1 plus chi H. Now this quantity 1 plus chi, if you how to draw this chi, so this is like X. Okay, X is like this. Here one is this, another is this. Okay, chi is this. So you curve one side of the X, it becomes like a bow and arrow. So this is a bow, this is the arrow. Okay, so bow and arrow figure, this is called chi. Okay, and mu naught 1 plus chi is actually given by another quantity which is called relative permeability of the medium. Relative permeability of the medium, and mu into mu naught into mu r actually is the permeability of that particular medium. So when you are having a given medium, say copper, iron, nickel, any medium is there, okay, each of them will have a separate mu r. Mu r is different for different materials. Mu into mu r, so same as electric field. If you remember electric field, epsilon r into epsilon naught was epsilon. We also call it dielectric constant, right? In this case there is no dielectric constant, it is just relative permeability. Relative permeability. Okay, mu r is equal to 1 plus chi is also a dimensionless quantity. Now this is also important formula, by the way. There was a question, this value is given, what will be value of this? So you need to calculate that. Okay, mu r is equal to 1 plus chi is a dimensionless quantity called the relative magnetic permeability of the substance. It is the analog of the dielectric constant in electrostatics. The magnetic permeability of the substance is mu, and it has the same dimension as units of mu naught. Okay, mu r equals to mu equals to mu into mu r, okay, or mu into 1 plus chi. So the three quantities chi, mu r and mu are interrelated. Obviously this is a constant quantity, this is a constant, so mu, chi and mu r, these three quantities are interrelated. Okay, if you know one of them, you can find the other. If you know chi, you can calculate mu r. If you know mu r, you can calculate mu. So any one of them is sufficient to calculate the other. Okay, these three quantities are not independent, they are interrelated, and only one of them is independent, given the other two may be easily determined. Okay, they cannot have separate values which are not coherent. If you know one of them, you can calculate back the other two values. Okay, now a solenoid has a core of material with relative permeability 400. The windings of the solenoid are insulated from the core and carry a current of 2 ampere. If the number of turns is 1000 per meter, calculate H, M, B and the magnetic current IM. Okay, now ignore the last part, magnetic current IM. Let's find B is given by mu Ni. Okay, the mu is obviously core permeability is mu naught. Okay, so it will be mu is mu r mu naught. Okay, mu r is given 400, mu naught we know 4 pi into 10 to the power of minus 7. Okay, windings of the solenoids are insulated from the core and carry a current of 2 ampere. So current here is given by I is equal to 2 ampere. Okay, mu is known, I is known, N is known. So you can calculate the magnetic field. Okay, so now how to calculate H? H is given by B by mu. So you don't want to do it actually. You can directly write this is as N into I. So the H is given by N into I. Now magnetization, how to calculate magnetization? Magnetization is basically M is equal to chi into H. Right, what is chi? Chi is 1 minus mu r into H. So if you just put 1 not 1 minus mu r minus 1 into H, put that, you calculate M as well. B is value already calculated. Magnetizing current is basically you need to compare it with mu naught Ni. Okay, so basically mu r I equals to I M. This is the magnetization current. Okay, if you want, you can calculate it. Just a problem that I have taken from your textbook. Try to solve it and let me know if you are having any difficulty solving this. Okay. Now, magnetic properties of materials. Another super important concept, which is basically the basic core of this chapter. From this, you are going to expect at least one question in your KCET paper. Okay. Generally, year after year, 1 or 2 questions come from this chapter. One of them is based on this portion. Okay, so there are 3 different types of materials. One is diamagnetic. Number 1 is diamagnetic. Diamagnetic substances are those which have tendency to move from stronger to weaker part of the external magnetic field. In other words, unlike the way a magnet attracts metals like iron, it would repel a diamagnetic substance. Okay, so that means what happens if you bring a, say, a iron piece near a magnet? Magnet will definitely attract the iron, right? But if you bring a diamagnetic substance, okay, for example, a copper is an example of a diamagnetic substance. Copper being a metal also, it's a diamagnetic substance. Okay, it will not be attracted, but it will be repelled. But the repulsion is very, very weak. It is very weak. You will not even feel the repulsion. Okay, unless the magnet is super strong, the magnetic field is super strong. In that case, you will feel that repulsion. Okay, if the magnetic field is very, very strong, in that case, you will feel the repulsion. Okay, so those materials are called diamagnetic material. One such diamagnetic material you may have seen an example, which is superconductors. Okay, superconductors at very low temperature. Some materials behave extraordinary, they show up extraordinary conductivity properties, and they are perfect diamagnets as well. Okay, so that's why there, if you may have seen an experiment, okay, it was very common few days back. So you have a circular magnetic track, and they have a frozen puff. Puff means puck, frozen puck. Puck means the game that you play in the table, that thing, similar to that, not that puck. Okay, but yes, it's a circular disc kind of a structure which is ice frozen. Okay, or by pouring some liquid nitrogen or liquid oxygen, it was frozen, and if you drop it on top of it, it will start rotating around it without falling. Okay, it will float on top of it. Okay, so that is this is a superconductor, this is a magnetic track, and it can move around it. Now we are trying to develop a technology which will transform our transport, and we will move like a Star Wars world. Okay, so it will be float on the air, and basically it's a superconducting thing, not the Star Wars exact way, but yes, somewhat similar. So basically it will float on the air, okay, without touching, so there will be no friction, so a lot of savings will happen there. The speed will be unimaginable. We can move very fast from one place to another, and the boundaries will be very small. You can imagine that you are traveling from Delhi to Bangalore in, say, 1 hour, faster than bullet trains. Okay, so that kind of technology, people are trying to do some research on it. If you study physics in future and become a low temperature physics specialist, maybe if you develop it, you might get a Nobel Prize. People are trying it. Okay, there are some advanced level of trials as well, but nothing concrete came up as of now. Some part experiments are happening. Okay, maglev trains are there, but not exactly based on this. So this is a new upcoming technology, maybe in another 20-30 years. The simplest explanation for diamagnetism is as follows. Electrons in an atom orbiting around nucleus possesses orbital angular momentum. Okay, now why diamagnets? Why diamagnets behave as they are behaving? Okay, so as I mentioned, each atom, okay, each atom has a positive nucleus and an electron. Okay, so electron is orbiting, say in this direction, electron is orbiting, it has a magnetic moment. Okay, so electrons in an atom orbiting around nucleus possesses orbital angular momentum. These orbiting electrons are equivalent to current carrying loop and thus possesses orbital magnetic moment. We already discussed it. Diamagnetic substances are the ones which resultant magnetic moment is in an atom is zero. So normally whatever the diamagnetic magnetic moment, so this is M here, suppose another M is there, another M there, another M there, so all of them cancel each other. The net magnetic moment in this substance is zero. Magnetization is zero. Okay, when magnetic field is applied, those electrons having orbital magnetic moment in the same direction slow down and those in the opposite direction speed up. So basically that means, suppose I apply a magnetic field, external magnetic field in this direction. This is the overall structure of the material. Okay, normally everything is zero. You apply an external magnetic field in this direction. The electrons which are orbiting in this side such that it was suppose magnetic moment, normally for what happens, this one fasten up, so this increases and the object moves in the direction of magnetic field. But what happens, this one slows down, so this value decreases, this value increases, so net effect in this direction increases, so they get repelled in the opposite direction to the magnetic field. Very interesting, right? So this electron which was providing the support in the direction of the external magnetic field, external magnetic field is there, I have to slow down, so it will slow down. It will slow down means its magnetic moment decreases. NIA, right? NIA, it depends on I and area. Okay, N is 1 for a single electron, is 1. So that electron slowing down means the current decreases. Current depends on the speed of the motion of the charge. So speed decreases, current decreases, magnetic moment decreases. What happens, and decreasing this is not only the one effect. The one which is moving in the opposite direction of the magnetic field, that one will fasten up, that will get energy, extra energy. You will say, I have to move faster. So what happens, in the opposite direction the magnetic moment increases. So the net effect in the opposite direction is high, and that's why the object moves in the opposite direction of the magnetic field. They repel each other. So opposite magnetic fields, they are repelling each other, and because of the repulsion it is moving in the opposite direction. Okay, clear? Next is paramagnet. So diamagnet is sorted. Now one important property of diamagnets I forgot to mention. Okay, every material, whatever material we are talking about, they are by nature, they are, everyone is diamagnetic. Everyone has certain level of diamagnetism. Every material has certain level of diamagnetism. Okay, so even if you are a good student, even if you are a class topper, you have a tendency that sometimes I don't want to study. That nature is everyone, that is a common thing. Okay, so even if you are thinking that only I am suffering from this thing, that I am not ready to study, I am not feeling good for studying, right? So every good student also have the same tendency in them, that they are also thinking that every day I will wake up, I will not study today. But their inner urge, their target, their dream is basically driving them to forward and make them study. Similarly, every material in heart, inside, they have a diamagnetic property. Okay, so they want to repel the magnet, but in some cases some other properties comes into the picture and they dominate it, and we see paramagnetic and ferromagnetic. Okay, so let's start with the paramagnetic. So paramagnetic substances are those which get weakly magnetized when placed in an external magnetic field. Okay, they have tendency to move from a region of weak magnetic field to strong magnetic field, that is, they get weakly attracted to a magnet. So basically it is exactly opposite. Paramagnets are exactly opposite of the diamagnet. Okay, diamagnets are repelling the magnetic field weakly, paramagnets are attracting the magnetic field weakly. Okay, weakly means not every week. Okay, so it is, the spelling is different, so it is not W-E-E-K, this is W-E-A-K. Okay, so it is weakly, not very strongly, right? So now paramagnet is, as I mentioned, they are also having some level of diamagnetic properties inside it, but the magnetization on the direction of the magnetic field is more than magnetization in the opposite direction. That's why they get attracted in the direction of the magnetic field. Okay, that is the basic reason of paramagnetic material. One such example is oxygen. Oxygen is a paramagnetic molecule. There is an explanation of how hybridization happens, etc. So this is a complicated explanation, but I am not going to do that. You can ask your chemistry teacher why oxygen is paramagnetic. You can ask your chemistry teacher, right? Next, ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. So ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. They have strong tendency to move from a region of weak magnetic field to strong magnetic field. That is, they get strongly attracted to a magnet, right? So ferromagnets are big boss. Okay, they are big boss, they attract everything, they are the strongest people. Okay, magnetic field is there, I am coming. Okay, so they are like, here magnet, stay there, I am coming, you don't need to move, like that. Okay, so they are the big annas. So ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. They have strong tendency to move from region of weak magnetic field to strong magnetic field. They get strongly attracted by the magnet. So iron piece, nickel, cobalt, they are the examples of ferromagnetic materials. Okay, now ferromagnetic materials, why do they behave like this? So for that we need to know a little bit about something called a domain theory. Okay, the individual atoms or ions or molecules in a ferromagnetic material possesses a dipole moment as in a paramagnetic material. So they also have individual dipole moments. Okay, however, so what is the difference between paramagnet, diamagnet and ferromagnet? So this is the basic picture. However, they interact with one another in such a way that they spontaneously align themselves in a common direction over a macroscopic volume called domain. So that means even though the molecular dipole moments are there, okay, they form small regional parties. Okay, so for example, this is a party only in this region, no one knows them. Okay, so if you go to some certain states, so there are a lot of hundreds of parties, political parties. Okay, they are limited to that zone only. Okay, so they here also similar thing. So this is one party, this is another party, this is another party. So they all have formed, even though they individually have certain things, but they align in a particular direction. So there are hundreds of molecules, thousands of molecules, they all have aligned in the same direction, but they are not in the same direction with another region, right? So they all have different directions. If you consider two consecutive zones, these zones are called domains. These zones are called domains. Okay, so basically because of their mutual interest, they all coming together and forming a particular direction, but obviously they do not, these two do not have any mutual interest, so they do not align. Now as soon as some external magnetic field comes, okay, then they all align in the same direction. Okay, thank you, we have to support this and form a government. So they all come together and forming the government. Okay, just a political joke, don't take it seriously. So when you are applying an external magnetic field, they all align in the same direction. Okay, they all align in the same direction. What happens when the external field is removed? So when you apply external field, they all align in the same direction, but when you remove it, in some ferromagnetic materials, the magnetization persists. So even if you have removed the external magnetic field, the alignment is still there. Okay, so they were misaligned initially. Now you applied external field, they all get aligned in the same direction, they all fall in line. Now even if the external magnetic field is gone, they still remain aligned in the same direction. Okay, such materials are called hard magnetic materials. They are called hard magnetic or hard ferromagnetic, both are okay, or hard ferromagnets. Alnico, aluminium nickel cobalt, is an alloy of iron, aluminium, nickel, cobalt and copper is one such material. So alnico, I was thinking only aluminium, nickel, cobalt. It has more than aluminium, nickel, cobalt, iron, aluminium, nickel, cobalt and copper. Okay, so this is an example of hard ferromagnetic material. Okay, next is the naturally occurring lodestone is another example. Okay, lodestone is a natural magnet. Such materials form permanent magnets to be used among the other things as compass needle. So they are basically some rare earth materials. They are super hard ferromagnets. Okay, rare earth magnets, if you may have heard the terms recently. Okay, rare earth magnets are basically hard ferromagnets. They are used in various parts. What happens? The external field is removed. There is a class of ferromagnetic materials in which the magnetization disappears on removal of the external field. Soft iron is one such materials, and they are appropriately enough called soft ferromagnetic materials. Okay, soft iron, the name soft iron actually comes from the fact that it is a soft ferromagnetic material. Okay, there are a number of elements which are ferromagnetic: iron, cobalt, nickel, gadolinium. Gadolinium is a very interesting material. Okay, it is at room temperature, actually it switches from para to ferro. Okay, para to ferro happens around I think, if I remember correctly, around 20 degrees Celsius. Okay, above 20 degrees Celsius it's a paramagnet, below 20 degrees Celsius it's a ferromagnet. So there, that portion of para ferro, how it happened, are not part of the syllabus, but yes, paramagnet can be converted into ferromagnet. So if you are wondering, yes, if you bring the temperature down, okay, then you can see that paramagnet can behave like a ferromagnet. Obviously every material has a certain temperature, okay, but yes, it is possible. So gadolinium is one such material. When I was doing my masters, I had a privilege of experimenting with gadolinium. Okay, the relative magnetic permeability is very greater than 1000. Now one comparison table that you need to remember before going into that, this is the comparison table. So for diamagnetic substances, the chi value is, susceptibility chi is between -1 to 0. So this is -1 to 0. For paramagnet it is 0. It is greater than 0 and less than 5 sigma. This value is very small value, say 1 or 2. Okay, it is a small value. This is a small positive value. Okay, so for diamagnetic substances, the susceptibility is between 0 to -1, so it is a negative value. Susceptibility is negative. So if you see that here, susceptibility is negative. Here susceptibility is positive but very small. Okay, here susceptibility is very larger than 1. So that is 100, 200, 400, 500, 1500. Any value which is very larger than 1 is considered ferromagnetic. Now relative permeability is between 0 to 1. It is between 1, it is greater than 1 and to another certain positive value, okay, and the relative permeability here is less than mu naught. This thing you never see in electrostatics. Electrostatics, epsilon naught was the smallest value. Any other medium will have greater than epsilon naught. But in case of magnetism, there are certain materials whose permeability can be even less than that of the free space, right? So that is one interesting point, just for a little bit of twist. Now mu is greater than mu naught, obviously, and here mu is super duper greater than mu naught. Okay, here epsilon is a small positive number. Now let's look into a question. In a permanent magnet at room temperature, domains are partially aligned. Now remember that when you are talking about domain theory, okay, the domains generally are perfectly aligned when you bring the temperature down. Okay, at around lower the temperature and higher the magnetic field, domains generally perfectly aligned. But if you are doing the experiment at room temperature, due to thermal vibration, actually ideally at 0 Kelvin, that is absolute zero, all domains perfectly aligned in the presence of magnetic field. But because there is no vibration among the atoms, but at room temperature, atoms the electrons are vibrating, so the domains cannot perfectly align. Okay, so in a permanent magnet at room temperature, domains are all partially aligned. Domains are all partially aligned. Okay, domains are all perfectly aligned is possible at 0 Kelvin temperature because there is no vibration, but at room temperature domains will not perfectly aligned, so it will be only partially aligned. This is a very important conceptual question. So remember that this is I think this is a PU level question, but you need to understand that. Now, if a bar magnet of magnetic moment capital M is cut along, I think I have solved it. I will not discuss that. Now, one deleted portion concept some of you might ask, for those, especially those who are preparing for JEE, sir, what is the time period of a oscillating magnetic needle? So you have a magnetic needle, okay, suppose north, south. If you just rotate it, it will move on a simple harmonic motion. Okay, and what is the simple harmonic motion? What is the time period of that motion? It will be 2 pi I by mb. This, based on this, there used to be questions coming in the past in KCET. We will see that once. So time period is given by 2 pi I by mb. I is moment of inertia, m is magnetic moment, b is external magnetic field. So there was one question that was came in the past. Okay, 2 pi I by mb. So this is the correct answer here. Okay, there is a no torsion in the suspension thread, then the time period of a magnet executing SHM. Okay, so this by the way is no longer part of the syllabus. This is the deleted syllabus, but if you are preparing for JEE along with KCET, then you need to remember it, because JEE this is not deleted. This portion is still part of the JEE syllabus. Okay, now this is not the end. We will solve a lot of questions, not only this one. We will be solving entire PUC model paper questions in this entire model paper PUC MCQ questions. Okay, not all the questions, MCQ questions we will solve. But before going to that, let's solve some KCET question. Which of the field pattern given below is valid for electric field as well as for magnetic field? So which of the pattern is valid for electric field as well as magnetic field? Now if you see that this one is for positive charges, this one is for positive charges, this one is for negative charges. Obviously monopoles do not exist. Now here if you see that this one, the central portion is not very clear. Central portion is not very clear, but may be possible. Now this one, this is a circular electric field. Circular electric field is possible in some cases, but circular magnetic field is definitely possible. So this one is not violating any principle. Here remember that in case of magnetic dipole, okay, if the fields are going out inside, it is going in the opposite direction. But for electric charges, so this is for north and south, okay, but for electric charges, this is going here and ending over here. Okay, so this line does not exist. So that means this line inside is non-existent for electric field, but this kind of magnetic electric field is possible. Okay, circular, no interaction between them. We know magnetic field can be circular, right? So that is what is important. Now we will be solving the MCQs. Let's start with one question first. But before I start with MCQs, just let me show you how can you join our free ACE KCET batch. So just go down in the description section of this video, enroll for 1 year complete KCET comprehensive preparation. Click over here, you will be redirected over here, and this is a 0 rupee batch. That means you don't need to pay anything. You just click on buy now, register yourself using your mobile number and email ID. And once you done, you will get the access to our free YouTube batch, and here you will get all the important lectures, then their class notes, PDF notes. Also you will get all the quizzes, assignments are here as well. You will get the assignments and quizzes as well. So some questions do have quizzes, so you will get everything on this without any money that you need to pay for it. Okay, assignments will be added very soon, so don't worry if you don't see assignments will be added. Quizzes are already getting added with the each of the chapters, so do that and join that batch by clicking on the description section. Now let us continue with our MCQs. So first MCQ, consider the following statements. Statement number 1, magnetic field lines do not intersect each other. If the magnetic field lines intersect, the magnetic field would not be unique at the point of intersection with reference to the above statements. So if you see that this is a statement number 1, which is very true. Obviously magnetic field lines do not intersect, so this statement is true. Okay, just let me change the color. So this is the correct statement. If the magnetic field lines intersect, the magnetic field would not be unique at that point of intersection. So this is the correct explanation of statement number 1 as well. If the magnetic fields, they intersect each other, then at the point of intersection magnetic field will have multiple direction, which is not possible. It will have only one unique direction, and that is not happening over here. That means both statements are true, and statement 2 is the correct explanation of statement number 1. Okay, remember this chapter is important for objectives. There are 2 1-marker questions that is going to come from this chapter. Maybe both of them are MCQs, who knows? So you have to practice MCQs from this chapter a little bit rigorously, so that you should not miss out on any MCQs coming from this chapter for your PU board, right? And if you are preparing for KCET, obviously from this chapter you are expected 2 MCQs anyway. Now, when the angle between the magnetic moment of a small compass needle and the uniform magnetic field in which it is placed is 180 degrees, the torque on the needle is maximum, the needle is in stable equilibrium, the potential energy of the needle is 0, the needle is in unstable equilibrium. So there are mainly 2 things they are talking about, torque and potential. Let's see what is a torque. Torque is mv sin theta. Here theta is 180 degrees, so torque is mv sin 180. Now sin 180 is 0, so it will be 0. Torque is 0. So the particle is in equilibrium. Whether it is a stable equilibrium or unstable equilibrium, that we have to find out. Now if torque is 0, obviously it is in equilibrium. Now it can be equilibrium in 2 positions. One is theta equals to 0, another is theta is equal to 180 degrees. So now here our job is to find whether it's a stable equilibrium or unstable equilibrium. How to do that? For that you have to find the potential energy. So what is the potential energy? Let me denote potential energy with U. That is mb cos theta. Okay, sorry, not mb cos theta. It is minus mb cos theta. Okay, this is the potential energy. Now what is the value of cos 180? Let's see that. So cos 180, that is minus mb minus 1, that is plus mb. So In fact, you can see that potential energy is positive and it is actually the maximum potential energy's value. So potential energy is maximum, torque is 0. So that means it must be a unstable equilibrium. If you remove it from the equilibrium position, it immediately moves from its equilibrium position. That's why it is called an unstable equilibrium. So there are 3 types of equilibrium. If you forget, let me remind you. So first is a neutral equilibrium. Neutral equilibrium means suppose a ball is resting on a flat surface. If you take the ball slightly left or slightly right, the ball would stay at its position, right? It will not move it. If you just switch it right or left, it will stay on its position. That's why it is called neutral equilibrium. So this is neutral, okay, equilibrium. Okay, so if you move an object slightly right or left, and if the object still stays in its original in the new position, so let me explain once more. Suppose you have a ball. If you take the ball slightly right or slightly left, okay, if the ball stays in its new position without trying to come back to its original position or go somewhere else, that kind of equilibrium is called neutral equilibrium. Okay, now if there are another type of equilibrium, if you take the ball slightly right or slightly left, and if the ball tries to come back to its original position, then it is called a stable equilibrium. This is called a stable equilibrium. Okay, now if you have a ball which is situated like this, if you take the ball slightly right or left, what will happen? Ball will say tata, goodbye, I will not come back to my original position, I will go to new position, I want to explore new position. So if you take the ball slightly right or slightly left, the ball will completely go in a different direction. This is called unstable equilibrium. This is called unstable equilibrium. Okay, so equilibrium title is there anyway. So this is the 3 types of equilibrium in nature. Now let's go back to our situation here. Obviously in case of stable equilibrium, potential energy is minimum. In case of unstable equilibrium, potential energy is maximum. Neutral equilibrium, potential energy is not that important. So definitely here, as you can see, the potential energy is maximum. By default, potential energy is negative, but here it is positive. That means it's the maximum value, and that means the needle is in unstable equilibrium. Important question, important concept as well. Now let's move on with the next question. A magnetized needle placed in a uniform magnetic field in general experiences both torque and a force but no torque, a torque but no force, neither force nor a torque. So if the magnetic field is uniform, it will experience equal and opposite forces. So net force will be 0, but there will be a torque. Net force will be 0. So net force will be 0, but torque will be mb sine theta. Okay, it is not 0, it is dependent on theta, right? So that means there will be a torque but no force. There will be a torque but no force. Let's move on with question number 4. When a freely suspended a magnet comes to rest in the direction. So if you suspend a magnet, it comes to a rest north and south, right? So it points south, it points north, right? So it comes to a rest in north-south direction. Nothing else. Easy question. Just answer it and move on. Next question. According to Gauss law in magnetism. Here it is Gauss law in magnetism, not electrostatics. Magnetic flux through a closed surface may be non-zero. Magnetic monopoles do not exist. There can be sources of sinks in magnetic field. The magnetic flux through any surface is 0. Let us understand that. So magnetic, even though it is too much appealing that magnetic flux through any surface is zero, actually Gauss's law do not talk about any surface. So make sure that you do not blindly mark this as correct, because Gauss's law is always applicable to one and only thing, that is closed surface. Okay, so this kind of questions are tricky, and you might think, oh my god, I know that magnetic monopoles do not exist is the answer, but option D also appears to be very correct. So what should I do? Which one should I choose? Because in case of Gauss's law, it says B dot ds equals to 0. So it appears that okay, this looks more accurate. Actually it is not. Here it is mentioned any surface. Here it is mentioned any surface. So that is the catch. Any surface, for any surface Gauss's law is not valid. Gauss's law is valid for closed surface. So here the answer is, according to Gauss's law, magnetic monopoles do not exist. If that had happened, B dot ds would not be equals to 0. Okay, it would have been same like magnetic field divided by mu naught, or mu naught into magnetic field, like that. Okay, it would not be 0. Right, in electric field it was q upon epsilon naught. It maybe in this case, if magnetic monopole would have existed, it will be mu naught into monopole strength. Okay, but that is not happening. So this is the correct statement, not this one. So make sure you understand the question, read it carefully if you have doubt, and eliminate the wrong options properly. Right, next is the dimensional formula for magnetic intensity. So magnetic intensity H, magnetization M, all of them have same dimension, AL to the power -1. Okay, unit is ampere per meter. So here the answer will be L to the power -1 into A. Right, L to the power of -1 into A. Next, the magnetic susceptibility of a material is 100. Its relative permeability is. So relative permeability, if you recall our theory, let me take you back to the theory once more if you have forgotten. Okay, so this is the theory that relative permeability is 1 plus susceptibility. So this is susceptibility, this one is called susceptibility, and this one is relative permeability. Just a second. Right, so if you go back to our question once more, you will see that here the given susceptibility is given, relative permeability you need to find. So what will be the answer? So it will be 1 plus chi equals to mu r. So here chi is given, susceptibility is given, so that is 100. So 1 plus 100. I made a small mistake. It will be 1 plus chi. So it will be 1 plus 100. That is mu r. So mu r equals to 101. Make sure you do not make a mistake. Sometimes students get confused whether it is 1 plus chi or what is chi, what is mu r. So make sure you remember that mu r is the relative permeability and chi is susceptibility. So answer here will be 101. Okay, not 99. 99 and 101. Even though close, you have to answer the correct answer. For which one of the following substances the magnetic susceptibility is low and positive? It has to be low and positive. That means what? It has to be a paramagnetic substance. It has to be a paramagnetic substance because it's positive. If it is negative, then it could have been a diamagnetic. Now here obviously bismuth is not a paramagnetic. Okay, copper is diamagnetic, iron is ferromagnetic, sodium is an example of highly paramagnetic substance. So this is the answer. Copper, as I mentioned in my lecture, if you are following the lecture from the beginning, copper is an example of diamagnetic. Bismuth is being neither a metal, neither a non-metal. It is something in between. So it is not a paramagnetic, it's a diamagnetic as well. So bismuth and copper are diamagnetic. Iron, on the other hand, is the ferromagnetic substance. Only sodium is the example of paramagnetic substance over here. In the following table, column 1 lists magnetic susceptibilities and column 2 lists some magnetic properties of the substances. Okay, you have to match 1 and 2. Diamagnetic substances, paramagnetic substances, ferromagnetic substances. Okay, now properties mentioned: mu is less than mu naught, domain formation, and chi-m is greater than 1. So susceptibility is greater than 1. So what is the correct match? So if you remember, ferromagnetic substances, they have domain formation. Only ferromagnetic substances have domain formation. Now in case of diamagnetic substances, the permeability is less than permeability of free space. So A is directly matched with P, and paramagnetic substances have chi-m slightly greater than 1, not super greater than 1. For ferromagnetic it is super greater than 1, but for paramagnetic it is just greater than 1. So option A is with P. So matching is A with P, A with P, B with R, and C with Q. So A with P, B with R, C with Q. So this is the correct match. So option B is the correct answer for this question. In case of match the following type of questions, if you are not sure which one to match, what you should do, you should at least try 1 or 2 of the matches possible. Okay, some cases only 1 is sufficient, some cases you require 2 of them to match. Okay, so based on that you can guess the final answer. Match the following type of questions are getting super popular, not only in your PUC as well as in your KCET exam, so you need to practice them as well. So let's continue with the next question. The atoms in which kind of magnetic materials have permanent magnetic dipole moment? Permanent magnetic dipole moment: only diamagnetic, only paramagnetic, only ferromagnetic, both para and ferromagnetic substances. So permanent dipole moment present in both para and ferromagnetic substances. Para, even though it is weak, but they do have a permanent dipole moment. Okay, atoms do have permanent dipole moment. Next, which magnetic property is a strong effect? Okay, strong effect means if you are doing something that shows strong reply. Okay, the paramagnetism, diamagnetism, ferromagnetism, both para and ferro. Now here the answer is only ferromagnetism shows strong effect. When you bring a external magnet, it gets attracted strongly. Okay, otherwise if you see the properties, para and dia, they get one is getting attracted weakly, another one is getting repelled weakly. So they are showing weak properties, but ferromagnets are strongest of them all. It shows the strongest property. So strong effect is only ferromagnet, not para and ferro. So that is also a critical question. So you need to think a little bit more when you answer certain questions, right? Next, if a magnetic substance is kept in a magnetic field, then which of the following substance moves out of the magnetic field? Again, here it is basically refers to the weak repulsion of the magnetic field, and we know that diamagnetic substances getting repelled weakly, so it will come out of the magnetic field. Repulsion, only repulsion can make it move out of the magnetic field. So that means only diamagnetic substance will move out of the magnetic field, not para, not ferro. Ferro and para both move towards the magnetic field. Para moves slowly, ferro moves very, very quickly. Okay, so remember this. So this question can be asked in terms of para. They will say that which one will move very slowly inside the magnetic field. Answer will be paramagnet, right? Now, next question, the ratio between magnetization and magnetic intensity. Okay, the ratio between magnetization and magnetic intensity is called permeability, is called relative permeability, is a dimensionless quantity, is the reciprocal of susceptibility. Let's see. So we know that magnetic intensity is chi m. Okay, magnetic intensity is chi into magnetization. So here they are talking about ratio between magnetization and magnetic susceptibility, magnetic intensity. So ratio between magnetization and magnetic susceptibility is 1 by chi. Okay, so it is a reciprocal of susceptibility. Right? Yes. So this is the reciprocal of susceptibility, and the correct answer is option D. Even though this is a dimensionless quantity, this is also a dimensionless quantity, but answer is option D. This is the reciprocal of susceptibility. Okay, but yes, it is also a dimensionless quantity as well. Next question. A compass needle of magnetic moment M is placed in uniform magnetic field B such that the angle between them is theta. The ratio magnitude of the torque on the needle and potential energy of the needle is proportional to. So what is the torque acting on a magnetic needle? It is mb sin theta. What is the potential energy? Minus mb cos theta. Now it says that the ratio of magnitude of torque is this. So magnitude of torque divided by potential energy is mb sin theta. Sorry, mb sin theta by minus mb cos theta. So mb cancels, you get minus tan theta. So this is proportional to obviously tan theta. Okay, in the answer there is no negative is mentioned, so we just take tan theta. So correct answer is option C, tan theta. Next, the following figure shows a small magnetized needle P placed at a point O. The arrow shows the direction of its magnetic moment. The other arrow shows different positions and orientations of the magnetic moment of another identical magnetized needle Q. Which one of the following statement is false from the above configuration? Okay, so let's see, almost the same question that we have answered in our lecture, only the options are slightly different. Okay, so here we have two magnetic needles. One is P is pointing in the upward direction, so this is fixed, P is fixed. Okay, and we have different orientation of Q's. Okay, Q have different orientation. Now first step is to remember that go back to our original electrostatic field. So suppose we have a positive over here, we have a negative over here. Okay, the magnetic field, the dipole moment is in this direction. Okay, so along the axis the dipole moment is in the direction of the magnetic moment, and along the perpendicular bisector the dipole moment is opposite to that of the P. Now rotate this structure like this. If you rotate this structure like this, what you will see that P is this. So this is the P. Okay, along the axis the dipole moment is always in the direction of the electric field was in the direction of the dipole moment, and here it is in the opposite direction in the perpendicular bisector. Right? This is the perpendicular bisector. Now use the same thing for a magnetic dipole moment. My magnetic dipole will behave same as electric dipole. Okay, only the symbol will be changing, that is it is M. Everything else is same as electric dipole. So this is the magnetic field. These are the magnetic field. Okay, these are the magnetic field. So this is the source. This one is creating the magnetic field. Now you are keeping Q at different location. So if you keep Q, for example, let's take this one, Q4. Q4 is taken in this direction. This is the direction of Q4. Okay, so what is the angle between magnetic field and Q? The angle between magnetic field and Q, theta equals to 180 degrees. Okay, theta equals to 180 degree means what? This is a unstable equilibrium. Similarly, next one is Q6. Q6 theta is 0. This is a stable equilibrium. This is unstable. This is stable. Now next one is Q5. Q5 is in this direction. So these two will also be unstable. Okay, and the other one is Q3 downward, Q3 in this direction. This will be a stable. So what we need to find is this one, just only to identify the magnetic field's direction. Okay, once it is done, its job is done. We do not need to consider this magnetic needle anymore. Okay, we only need to identify, okay, this is the primary source. Because of this, what will be the direction of magnetic fields along its axis and in the perpendicular bisectors. Once that is done, now we will only take the magnetic field and the second needle, find their angle and say what type of equilibrium it will be. Now there are two modes, Q1 and Q2. Q1 is in this direction, Q2 is in this direction. In both cases, theta is 90 degree. In both cases, theta is 90 degree. So theta 90 degree means torque is not zero. Actually, torque is maximum, but potential energy is zero. So these two are, Q1 and Q2 are not equilibrium. So Q1 and Q2 are not at all in equilibrium. So these two positions are not equilibrium. Okay, this is also not in equilibrium. Always use the formula torque equals to mb sin theta and potential energy is equal to minus mb cos theta. Okay, initial first needle is only to determine the magnetic field around this needle. Once it is done, then only you will be able to apply these two formula. And if the torque is zero, it is equilibrium, but potential energy, if it is positive, it is an unstable equilibrium. If potential energy is negative, it's a stable equilibrium. Okay, got it? So here let's see the options. In configuration PQ1 and PQ2, the system is not in equilibrium. This is a correct statement. So we have to find a false statement. So statements are different. Exactly the same question you have solved, but the options was different. Here options are different. The system will be in stable equilibrium for configuration PQ3 and PQ6. So PQ3, what is Q3? PQ3, that is this one, and PQ6, I think this one. PQ6 and PQ3, these are a stable equilibrium. So this is also correct statement. Next is the system will be unstable equilibrium for configuration PQ4 and PQ5. So PQ4, what is PQ4? PQ4, this one, and PQ5, the system is unstable equilibrium. So this is also correct statement. So back to back, top three statements are correct. So this is a very tricky question. It's actually a KCET level question. This question is a KCET level question. Okay, not super PU level question, but this is a KCET level question. PU6 corresponds to maximum potential energy state among the given configuration. So PQ6, if you come over here, PQ6 has a theta equals to 0. So that means potential energy is minus mb, cos 0 is 1. Right? So potential energy is actually corresponds to minimum potential energy, not maximum potential energy. So this is false statement. So this is the correct answer for our all the questions. Understand this question. This is one question is super important, and if you solve this question on your own, then your all the conceptual clarity about similar questions, maybe about electric dipole or about magnetic dipole, will be resolved. So understand this problem by heart so that you actually will be able to answer similar questions which might be asked in the upcoming exam. So very, very careful about this. Now another easy question. Needles N1, N2 and N3 are made of a ferromagnetic, a paramagnetic and a diamagnetic substance respectively. A magnet, when brought close to them, will attract N1 strongly but repel N2 and N3 weakly. Attract N1 and N2 strongly but repel N3. So let us understand needle N1, N2 and N3 are made of ferro. So N1 is ferro. Okay, N2 is para and N3 is dia, right? So if you brought a magnet, okay, what will happen? So this will be strong attraction, this will be weak attraction, this will be weak repulsion. Okay, so N1 will be attracted strongly, N2 weakly, and repel N3 weakly. So option C is correct. Okay, N1 will be attracted strongly, N2 will be attracted. Let me change the symbol once. Okay, so that you don't get confused. So this will be attracted strongly. Attracted means arrow is this side. Okay, this will be weakly, this will be also attracted but weakly, this one will be repelled but weakly. Okay, so N1 and N2 will be attracted weakly, one is strong, N1 is strongly, N2 is weakly, N3 will be repelled. So answer C is correct answer. Next, when a bar magnet is suspended freely, it points in the direction north-south. Same question, only the options are different. Okay, so it will always point north-south direction, no matter whatever is the option given in the question. You should always choose north and south. The ferromagnetic material among the following is copper, nickel, lead, calcium. So nickel is a ferromagnetic substance. Copper is a diamagnetic, lead and calcium are paramagnetic. Okay. Next, the physical quantities related to magnetism are listed in column 1 and dimensions are listed in column 2. Identify the correct match. Magnetic field, magnetic permeability, magnetic moment. Okay, now out of these, the easiest one is magnetic moment. Magnetic moment is current into area. In fact, it is National Investigative Agency. Now N is just a number, it has no unit. So when it comes to the dimension of magnetic moment, it comes out to be AL square, right? This is A, this is L square. A is area here. Okay, remember I is A is L square. Okay, so when we are denoting something normal variables and when you are denoting the dimensions, they are different. Okay, so current is replaced by A and area is replaced by L square. So magnetic moment is matched with this one. Okay, and now because it's a little complicated, what we will be doing, we will see that if there is a unique match for 2 with B or not. So if you see, we are lucky here, only one match with 2B. Okay, 2A, 2A, 2C. So obviously we are lucky. So that is what I am talking about, always talk about, always suggest my students, try to find at least one unique match. If you are successfully do that, then your problem will be solved. So definitely 2B is correct, we are sure. That means option A is correct. Now let's look into the other matches. So magnetic field is matched against this and magnetic permeability is matched against this. Okay, so this is the tricky option. So most students will tend to match 1 with C and 2 with A. So then they will make mistake. Okay. Sorry, I made a mistake. Sorry, my mistake. Option 3 is matching with B. Option 3 is matching with B. So this is the correct answer. Option 3 is matching with B. Sorry, I know many of you are crying right now, sir, what you have done. Yes, sorry. So that is a big blunder from my side. Okay. So 3 is matching with B. So 3B is also a unique match. 3B is also a unique match. So magnetic field will be matched against C, this one, and magnetic permeability will be matched against A. The whatever the common matching logic says, that is correct. Okay, sorry, my mistake. Now let's move on with next question. Statement 1. the net magnetic flux through any closed surface is 0. This is the Gauss's law of magnetism. The number of magnetic field lines leaving the surface is balanced by number of lines entering it. If you recall, just some few minutes ago, 30-40 minutes ago, we did discuss that even if there is a, suppose we have a only one magnet inside, okay, some field lines are exiting it, okay, but they are coming back from the magnet, okay, from the magnet. That means the net field line that is crossing the surface is 0. That's why no matter even if you cross one pole, the magnetic flux will still be 0. So that means both statements are true and 2 is the correct explanation. So both statement 1 and 2 are true and 2 is the correct explanation for 1. So that is a very interesting statement based question. Next, the susceptibility of a ferromagnetic system. Susceptibility of a ferromagnetic substance, whenever you see a ferromagnetic here, that means it will be very greater than 1. Okay, as many varies as possible. So here it is very greater than 1, right? For ferromagnetic material, susceptibility is very high. Now, next, which of the following properties is false for a bar magnet? It does not produce magnetic field. Its poles cannot be separated. So it does not produce magnetic field. It is obviously a wrong statement, completely false statement. So this is the correct answer. So if you read the option, first option itself, even though you just read the options, sometimes you feel, oh, what is the correct answer? After reading all 4 options, right? We always think, oh, what is the correct answer? So don't worry, first option itself is the wrong answer. Poles cannot be separated is true. You cannot separate the poles. It points north-south direction when suspended is also true. It's like poles repel and unlike poles attract. This is also true. So all remaining 3 options are true. Only it does not produce magnetic field is wrong. It does produce magnetic field. It does attract other magnetic materials around it as well. So this is a wrong statement, right? Whenever you are in doubt, okay, after even if it says wrong, true or false, first of all, you need to figure out it is true or false. So that is one very trick. Which of the following is wrong, which of the following is correct? Following is correct is still the normal question, right? Which of the following is true? That is normal question. But if they say which of the following is false, then the confusion starts, because there will be 3 correct options. 3 options will be correct statements. Only one wrong statement is incorrect. So that wrong statement you have to find and mark it. So that is what makes these kind of questions little tricky. Okay, again, obviously after each and every question you answer, check the options once for your confirmation. Okay, as susceptibility of certain magnetic material is 400. What class of the magnetic material it is? So susceptibility is 400. What is this number? Is it very small, slightly greater than 1, or it's larger than 1? It is very larger than 1. Okay, susceptibility is very larger than 1, so it must represent a ferromagnetic substance. It must represent a ferromagnetic substance. If it is 1, 2, 3, 4, if it is 4, it could be a paramagnet. Okay, but because it's a 400 is much larger than 1, then it must be a ferromagnet, right? Next, the magnetic field lines inside a bar magnet. So if you remember, just now I draw the diagram. So outside the bar magnet, magnetic field lines run from north to south. Inside the bar magnet, it is south to north. So if you forget that, outside the house, your father dominates everything, right? Father is the most renowned person, but inside your home, your mother dominates everything. Similar to here as well. Okay, outside the field line starts from north to south. Inside it is south to north. So that means it is inside the bar magnet, it is south to north. Okay, from south pole to north pole. Okay. Next, when a bar magnet of dipole moment M is placed in a uniform magnetic field B, then what is the expression for the torque? Then torque is okay, that statement is missing here. So the torque is given by Remember, torque acting on a magnetic dipole is given by M cross B. It is M cross B, not B cross M. So correct answer is M cross B. Okay, minus M dot B is the potential, and M cross B is the torque, not minus M cross B, not B cross M. So be careful about that. Next, the SI unit of magnetic flux. So what is magnetic flux? SI unit of magnetic flux is Weber. Okay, we will discuss more about in the next chapter anyway. So magnetic flux unit is Weber and Tesla meter square. Tesla meter square or Weber. Okay, so magnetic flux is given by magnetic flux is given by magnetic field into area. Magnetic field into area. So this is the in case of Gauss's law, if you remember the statement of Gauss's law, it says that the net magnetic flux coming out through a closed surface is 0. Right, net magnetic flux coming out of a closed surface is 0. But if the surface is not closed, magnetic flux will not be 0. Okay, magnetic flux is 0 only for closed surface. If the surface is not closed, magnetic flux will be not 0. Remember this very important statement. Okay, universal property among all substances. Universal property among all substances is diamagnetism. Right, we have seen that universal property, all para, ferro and dia, every one of them have diamagnetism as common. Okay, even para has certain level of diamagnetism, ferro also have a certain level of diamagnetism, but in these materials the other properties, paramagnetic properties dominates diamagnetic, ferromagnetic property dominates diamagnetic. Okay, so they are already there. Okay, if you remember Harry Potter movie, at the last part of the Harry Potter movie, there was a small part of the evil Voldemort is residing inside Harry Potter. Similarly, so this is the evil part which resides inside paramagnet and ferromagnet, no matter how powerful they are. Okay, so this is the small part of Voldemort which is hidden inside each of these materials. Right, now next question. Magnetization of a sample is magnetic moment per unit length, magnetic moment per unit area, magnetic moment per unit volume, magnetic moment per unit current. So magnetization is given by magnetic moment per unit volume. Okay, net magnetic moment, actually correct word should be net magnetic moment. So net magnetic moment per unit volume, that is called magnetization. Okay, so this is the magnetization of a sample. Next, the magnetic flux through any closed surface is 0. This is in accordance with Gauss's law in magnetism. I was discussing just when we are discussing the magnetic flux, the unit of magnetic flux, etc. So that is Gauss's law of magnetism. Two more questions. In a permanent magnet at room temperature, domains are, so in a permanent magnet at room temperature, domains are not perfectly aligned no matter what. Okay, it is not a perfect magnet, it's a magnet, but it's not a perfect magnet. Domains are partially aligned. Okay, domains are partially aligned at 0 Kelvin. Okay, at 0 Kelvin, that is absolute 0, domains will be perfectly aligned. Okay, otherwise there will be vibrations of the electrons, vibrations of the atom. Okay, and that's why the domains will not be able to perfectly align. But yes, at 0 Kelvin, electrons do not vibrate, they just rotate in their fixed path as provided by the model, right? Bohr model is one of the basic model. Okay, there are more advanced model than that. So according to the atomic model, electrons just orbit in their path, they do not vibrate now. So that is at 0 Kelvin, domains are perfectly aligned. Last question, needles N1. Okay, I think this one is, I have discussed it once more. Let's see, N1, N2, N3 are made up of ferromagnet. Now, so this is N1 is ferro. Okay, N2 is para. We know the drill, just practice. N3 is dia. Okay, now you brought a magnet. It will be strongly attracted. This will be weakly attracted, and this will be weakly repelled. Okay, so N1 attract N1 strongly, repel N2, and attract N1 strongly, N2 weakly, and repel N3 weakly. So option B is correct. If you read the options are slightly different than the previous question. Okay, so make sure you read the options carefully before answering. Now before I go, I just want to remind you once more, if you go down in the description section of this video once more, you will find the link to join our free KCET batch. Okay, enroll now for 1 year complete comprehensive preparation. Join free ACE KCET 2027 course. So click over here, and here you will get the free batch for 0 rupees. Once you register yourself, you will land on our course page. Okay, and from the course page you can start learning as you want. Okay, if you see that here some blink is there, so live and upcoming, whatever is coming over here, ongoing, upcoming, etc., will also be added over here. So all the tests are here, so you can check continuity and differentiality. Past test was electric charge in KCET, so this is also being there. So the test I was trying to show you that time, it is already over. Okay, so 20th August 5 p.m. you will get the notification whenever it is coming. Okay, if it is there, okay, in the notification section as well. So currently mathematics test is going on, so register yourself. You will also get the support of Ved. You can see Ask Ved popping up over here. You can ask Ved AI your doubts, questions. It will answer your doubts and questions as well, right? So what are you waiting for? Join today and you will get this PDF and all the other PDFs that we are doing on our channel, right? So I will see you in our batch very soon. Till then, bye.